notice you have seen this before and that. So far, we have looked at all of these formulae here, all of them, but we are not yet finished. We need to learn how to resolve two forces at right angles using calculations. That can be done by scale drawing, but CXC wants you to be able to do this by calculation. So the resultant of two forces which are at 90 degrees to each other. Now before we get to that, if you have two vectors that are in the same direction, for example, 400 newtons and 600 newtons both acting due east, just add them arithmetically, so that will be 1000 newton due east. On the other hand, if you have two forces that are exactly opposite to each other, you will subtract the smaller from the larger arithmetically, and the resultant will be in the direction of the larger force. For example, if 400 newtons, like that, is due west, and 600 newtons, like that, is due east, then their resultant will be 600 minus 400, which would give us 200 newtons due east. Now we come to the situation where the two forces are perpendicular to each other. Now you can use the cosine and the sine rules to do that. However, there is an easier method, and that is to use Pythagoras Theorem to find the magnitude of the resultant and one of the three trigonometric ratios to find the direction. But first we need to know what is Pythagoras Theorem, and we need to know what are the trigonometric ratios. Pythagoras Theorem applies to right angle triangles only. Now we need to know that if we have a right angle triangle, as in the case of this one here on the left or this one here on the right, that the side exactly opposite to the right angle is called the hypotenuse. Pythagoras theorem simply states that the square of the hypotenuse is equal to the sum of the squares of the other two sides. So if you have a triangle like this side down here is 4 centimeters, this one is 3, this one up here must be 5 based on Pythagoras theorem. If you square this side here, now remember that side there is the hypotenuse. If you square this side here, as you can see, we have 16 square units. If you square this side here, as you can see, we have 9 square units. If you add them up, you get 25. If you were to square the hypotenuse, you will also get 25. So the square of the hypotenuse, which is 25, is equal to the sum of the squares of the other two sides. 9 plus 16 will also give you 25. If this angle here is angle A, then this side over here is lowercase a. We already know that. And since this angle here is B, then that side over there is lowercase b, and up there is C. Then this side down here is lowercase c. So if we are going to use these letters indicating the sides, then what we have is a squared, this side, is equal to b squared plus c squared. This formula has 3 variables, a, b, and c. If you know any two, the third can easily be calculated. So let's look at an example. A, b, and c. If b is 8.00 centimeters and c is 10.0 centimeters, and you want to find a, then we know that a squared is equal to b squared plus c squared. If we remove that square from there, we get a is equal to the square root of all of that. And we substitute the numbers we are given, 8.00 squared plus 10.0 squared. We work that piece out. We get a is equal to the square root of 164. And when we put that in our calculator, we get 12.8, and we are using 3 significant figures. And so our uncertain digit is here. Half of that is 0.05. Or you can state that as 12.8 centimeter correct to 3 significant figures. But CXC prefers that format. Let's look at another example. A, B, and C. This time we know C and we know A. We want to find B. So our formula says A squared is equal to B squared plus C squared. We change that around and we make B the subject of the formula. So B is equal to the square root of A squared minus C squared. We substitute the numbers we are given. 15 squared minus 12 squared. We get the square root of 81, which is 9.0. We are using 2 significant figures. So our uncertain digit is here. Half of that position is 0.05. Or we can state it as 9.0 centimeters correct to 2 significant figures. But remember, this is the format that CXC prefers. Now, you need to be careful because when you find the square root of 81, you will get 9, exactly 9 from your calculator. But we are using 2 significant figures, so we add a 0.0 to make it 2 significant figures. Let's look at a simple example. A swimmer swims directly across a flowing river that is 50.0 meter, 3 significant figures. Because of the action of the water current, the river current, she is swept 12.0 meters, 3 significant figure, downstream from the opposite shore at which she started. How far did she swim? Well, we need to draw a sketch which will look like this. This is the river here. The water is flowing in that direction. She starts out at B here, intending to go to A, but this current pushes her slightly off track. She ends up at C, and the distance from here to there is 12 meters. Okay, so now we know if this here is A, this side over here is C because that angle there is C, and this side of this angle over here is B, so that side is B. We know A squared is equal to B squared plus C squared. We want to find A. A is equal to the square root of B squared plus C squared. We substitute the numbers we are given, and we eventually come up with A is equal to 51.4 plus or minus 0.5 meter, and that's because we are using 3 significant figures. CXC requires that answer as opposed to this one. Let's look at another example. A plane took off from G and flew 400 kilometers north to R. From R, it flew west to Q. If the direct distance from G to Q is 700 kilometers, how far is it from R to Q? So we will make a little sketch. Recall that this direction is north and this is east. The plane took off from G, flew north to R, which is 400 kilometers, and then from R flew west to Q. We don't know that distance. That is what we have to find. But we do know from G to Q is 700 kilometers. Okay, if that side there is uppercase R, then this side here is lowercase r, which is our hypotenuse. So we can write r squared is equal to g squared plus q squared. We want to find g. We want to find g over here. We rearrange this formula to make g its subject, and we get this. G is equal to the square root of r squared minus q squared. We substitute the numbers we are given, and we work it out, and we come up with 574 kilometers, but we are only allowed one significant figure, so we have to round off at this 100 position. So our answer will be 600. Half of the 600 position is 50. So 600 plus or minus 50 kilometers. Two forces, 430 newtons and 760 newtons, act at a point at an angle exactly 90 degrees to each other. Calculate the magnitude of their resultant. That's the first thing we have to do. And in a little while, we will also have to calculate the direction. So we draw a sketch. So this is one of the forces acting this way. We will let that be the larger force, 760 newtons. This is 90 degrees, 430 newtons. So that's 90 degrees. So we complete this rectangle, which is the same as completing the parallelogram. And we draw the diagonal from here to over there. But this time, we are going to calculate this based on the fact that this is 90 degrees. So we will use Pythagoras Theorem. We want to find A, the magnitude of the resultant. We will let this side over here be B, and that side over there be C. So we know that A squared is equal to B squared plus C squared. We remove the square from here. A is equal to the square root of this. We find the square root of A, and we get 873.21 newtons. Of course, we are only allowed two significant figures, so we round it off here. So that gives us 870, and since we are rounding off at the tens position, we take half of that position, which would give us 5. So 870 plus or minus 5 newtons. So that is the magnitude of the resultant only. We haven't found the direction yet. Now we can use Pythagoras Theorem to find the magnitude as we just did, but now we also need to find the direction, since a vector has both magnitude and direction. So to do that, we could use one of the trigonometric ratios. So we will spend a little time understanding what the trigonometric ratios are. So this is a right angle here. If we consider this angle here, which we will call theta, the sine of this angle is the ratio of the opposite side to the hypotenuse. So you sometimes say it as this: sine theta is equal to opposite over hypotenuse. Now bear in mind that is a ratio. So if you find sine 30, as in this case, let us say that is 30, and we get 0.5, what that means is that the opposite side is always 0.5 of the hypotenuse at 30 degrees. If you increase that 30 degrees to say 45 degrees, and so the size of the opposite when compared to the hypotenuse at 60 degrees is 0.87. And if we take 89 degrees here, actually the two lines, the opposite and the hypotenuse, are basically the same. So the opposite is 0.9998 of the hypotenuse. And of course, at 90 degrees, you basically have one line merging with the other. So you don't even have a triangle. So in that case, the sine will be 1. That's the sine of an angle, is the ratio of the opposite side to the hypotenuse of a triangle. And the sine is never greater than 1. Here are some values for the sine. If you change this angle, if you begin at 0 and you go up to 90, notice that the sine begins also at 0 and it goes up to 1. Of particular importance is this 30 degrees, where the sine is 0.5, meaning that this side is 0.5 of the hypotenuse, and so on. Now we come to the cosine. Whereas sine was dealing with opposite to hypotenuse, cosine is dealing with adjacent to hypotenuse. So you may see cosine theta is equal to adjacent over hypotenuse. That means what fraction the adjacent is when compared to the hypotenuse. So let's look at some examples. So if this angle here is 30, the cosine of 30 is 0.87. That is to say, this side here is 0.87 of the hypotenuse. If we take the cosine of 45 degrees, this one here, we get 0.7. So when this angle is 45 degrees, this adjacent is 0.7 of the hypotenuse. If we take 60 degrees, if we allow this to be 60 degrees, then the ratio of the adjacent to the hypotenuse is 0.5. If we make this angle here 89 degrees, we notice that it is almost 0. And of course, if we make it 90, then the cosine of 90 is 0. So we really don't have a triangle. We can compare sine and cosine side by side here. Over here are the angles. And again, if you find the sine of 30, you will get 0.5, but the cosine of 30 is 0.866. Conversely, if you find the sine of 60, you will get 0.866, whereas the cosine of 60 is 0.5, and so on. At 60 degrees, this is, we're looking at sine 0.866 of that, opposite to hypotenuse. If we are looking at the cosine, then we're looking at the adjacent to the hypotenuse. And the cosine of 60 is 0.5. So at 60, this is 0.5 of that. That's a cosine. At 60 degrees, that is 0.866 of that. That's the sine. And you can look at the rest of the stuff. So we looked at sine, which is the ratio opposite to the hypotenuse. We looked at cosine, which is the ratio of the adjacent to the hypotenuse. Now we're looking at tangent. And the tangent is the ratio of the opposite to the adjacent. So you see tan theta is equal to opposite over adjacent. That is a ratio. So if this angle here is 30 degrees, then the size of the opposite when compared to the adjacent is 0.58. So this is 0.58 of that. And of course, if we change the angles, we make this angle here 45, then the opposite and the adjacent are the same. So you get 1. And if you make this angle here 60 degrees, then now this side here is longer than that side. So you get 1.73 and so on. Let's make sure we understand that. Tan 20 is 0.36. So this side here is 0.36 of that if the angle is 20 degrees. If the angle is 30 degrees, and we find the tan of 30, we will get 0.58. That is to say, this is 0.58 of that, whatever length it is. And if we go to 45 degrees, we will get an answer of 1. That is to say, this side here and this side here are the same. So whatever this is, let's say 5, this will also be 5. You divide 5 by 5, you get 1. If we make this angle 60 degrees, now notice that the opposite is longer than the adjacent. And so you will get an answer bigger than 1, 1.73. And of course, if it's 70 degrees, it is 2.75. And worse yet, if it's 80 degrees, notice that is much longer than this. Opposite is much longer than adjacent, and the ratio is 5.67. This is 5.67 times that. Of course, you find tan theta, you get infinity because you are asked to divide by 0. Now, this just compares all three at the same time. At an angle of 45 degrees, 45 degrees here, you find that the sine of 45 degrees is 0.707. That is to say, this side is 0.707 of that. If you find the cosine, then this side is 0.707 of that. And of course, if you find the tangent, because the opposite is the same as the adjacent, you will get an answer of 1. And so on. So now you understand the concept of the trigonometric ratios. We can go through this and do a whole bunch of other examples. So which one do you use? Now that we find the magnitude of the resultant, do you use the sine, the cosine, or the tangent? Let's look at this example. First, we will make a sketch. Finish making the sketch. We complete the parallelogram. And we draw the diagonal from the point of origin, which is this. This, of course, is A. We will let this side be B. We could let any side be B. And let this side be C. And so we know this is 54 because that is 54. We want to find this angle here. We know this is 90 degrees. We apply Pythagoras Theorem. So we want to find A. We know B and we know C. So A is equal to the square root of B squared plus C squared. You substitute that and you get A is equal to 92 newtons. So we know this is 92 newtons. Now you could have used the cosine rule, and I'll tell you why. You notice A squared is equal to B squared plus C squared, and then it continues with minus 2BC cosine A. But since this angle A here, this angle here, is 90 degrees, and we know that the cosine of 90 is 0, then this part of the cosine rule is removed. So let's look at that. A squared is equal to B squared plus C squared minus 2BC cosine A, which is what we used when the angle was not 90 degrees. But then, if we consider, as I said, this part here, cosine of A is, so that eliminates all of that. We get rid of it. And we are left with A squared is equal to B squared plus C squared. So Pythagoras theorem is actually a special application of the cosine rule. Sixth, we will use one of the trigonometric ratios to find this angle here. Now we know this is 92 newtons. We know that, and we know this. You can use the sine ratio because you know the opposite and the hypotenuse. You can use the cosine ratio because you know the adjacent and the hypotenuse. You can also use the tan ratio because you know the opposite and the adjacent. Now, I prefer to use the tan ratio, and the reason for that is simply that you are using original data. We are given B and we are given C. Now, if we use A, there's nothing wrong with using A, except if you had an error in creating A, then you would have a carrying over error in calculating this angle. Now, CXC will not give you completely wrong. CXC will deduct 1 mark for carrying over an error, provided you do the rest of the working for that part of the question correctly. So as I said, it's best practice to use your original data. And so we find that tan theta is equal to B over C, which is opposite over adjacent. Theta is equal to inverse tan, B over C, substitute that, and we get 36 degrees. So our answer is 92 newtons at 36 degrees from the 75 Newton force. Concluding thought on this, if you have two forces, say 40 newtons and 70 newtons, and they act at a point, the largest resultant you can get is 110 if they're acting in the same direction. And the smallest you could get is 30 newtons if they are acting in opposite directions. So when you do a question and you find that your answer falls outside of the 110 and the 30, so it's greater than 110, so you get 120, or you get 20, you know definitely that your answer is wrong. So you need to recheck it and make sure you have the correct working. CSEC also requires you to be able to explain that a single vector is the equivalent of two other vectors at right angles. This is actually the reverse or the inverse of what we have been doing. We were looking at two vectors at right angle and finding their resultant. Now in this case, we are given the resultant and we need to show what two vectors will give that resultant if those two vectors were from the end of this vector. You draw broken line horizontal like that and vertical like this. And then from this original point, you draw one force or one vector going like that until it touches that broken line, one going like that until it touches that. And those are your two original vectors at right angle that would give you this as the resultant. It's fairly easy to calculate too. So let's look at another example. Remember, we are looking at a single vector and we want to show how that is the equivalent of two other vectors at right angles. So let this be our single vector. If we drop a perpendicular like that and a horizontal, draw a horizontal like that, from this point, we draw a line going straight up like that and one going straight across like this. Those forces in blue would give the resultant in yellow. If we know that this is 22 and this angle here is 35, then we can use the cosine trigonometric ratio to find the adjacent side here, which would give us 18 newtons. We can also use the sine trigonometric ratio to find the opposite here, and that will give us 13 newtons. We could have used Pythagoras Theorem after we got this and this to find that. But remember what I said about using original data. We can use tan, but to use tan, we will have to use one of these calculated values. Yes, we can use a squared is equal to b squared plus c squared once we know the hypotenuse and one of the other sides. We can use that to find the other side. Or you can just simply use scale drawing. So there are several ways to show that a single vector is the equivalent of two other vectors at right angles. Now, CXC does not require you to do this, but it's pretty easy. As a matter of fact, those original forces don't have to be at right angles. Any parallelogram you can draw, starting from this point, with this as one of its diagonal, will actually solve the problem, but they will not be at right angles. For example, you can do this. If you have two forces like this, that one and that one, this one is the resultant. Or if you have two forces like this, that one and that one, that is the resultant. Or If you have a resultant like that, you could have a force like this or like that. And so you don't have to do this for CXC. I'm just saying that this is pretty straightforward. If you could do it for right angles, you could do it for any other angle. And that's it for section A, mechanics. We have covered those 17 equations or formulae. We have also looked at these as they relate to the right triangle. And I think we have accomplished a lot. That brings us to the end of the formula section for mechanics. We have covered a little over 50% of all the formulae that you need to learn and use for CSEC physics examination. Next, we will deal with section B, thermal physics. As just indicated, thankfully, we don't have that many formulae to deal with in section B.